This is the part 2 video where we dig in deeper to the types of crystalline solids. I know we come up with these images when we think of crystals. However, the majority of our world would be classified as being crystalline solid, even though we don't see everything in snowflake form and diamond form and so on. But if we would get on the particle level, these are the 4 different types of crystalline solids that we interact with throughout our day, throughout our world. The type of crystalline solid can be concluded by knowing the formula and the chemical makeup. So we already went through that. We can just look at the types of elements that make up our compound. But what distinguishes their properties are the forces that hold the particles together. So that's what this video will get deeper into. What are actually the types of particle attraction between these particles? Now first, what actually are the type of particles in our 4 different types of crystalline solids? Well, if it is ionic, the particles that take up the corners or possibly the center of the unit cell or the faces are cations and anions. So in the case of magnesium hydroxide, the cation would be magnesium +2 and the anions would be your hydroxide. In the case of metallic crystals, they are just metal cations. Covalent molecular, they're going to be atoms or molecules. So I didn't give you any examples of a covalent molecular that would just be made of atoms at the unit cell. But for example, if we would have solid neon, it would be neon atoms that would be taking up the position of the unit cell. So I'll add that to our examples. And then here, we just say they're going to be atoms of carbon in the form of graphite or diamond, atoms of silicon, and then bonded to atoms of oxygen. So these would be atoms as well. Okay, so these are what you need to imagine take on the structural positions that eventually give us our crystal lattice. All right, when ionic, remember what we learned about bonding. Well, what holds cations and anions together throughout the ionic crystal is electrostatic attraction. That is the natural pull of positive for negative things. So, if we have sodium chloride, we know it forms on a cubic unit cell. If this is a chloride ion, it is not just attracted to this sodium. It's also attracted to this sodium, and the one maybe here. And then this would be attracted to this chloride and so on. So it's a network of electrostatic attraction that extends throughout the entire crystal lattice. Remember, electrostatic attraction is pretty strong. So this is going to be, pretty strong, which will impact the characteristics from there. Metallic, okay, that is a sea of electrons. And so if you have iron atoms in a section of an iron nail, depending upon the charge this takes on, let's say that each of these iron donate 2 electrons to be mobilized or delocalized. These will be positive 2s. Now, they need the electrons there to remain electrically neutral, but they don't have a specific home, so they're free to move. Well, it's those sea of electrons that gives the unique characteristics to metals. But in essence, it's kind of a weak electrostatic attraction. This has a range of strengths. We would generally categorize the pure electrostatic attraction of ionic to usually be a bit stronger than in metallic, but there can be very, very strong metallic crystals, and then some that are, a little weaker, and the properties will reflect that. Covalent molecular. Okay, these are going to be atoms or molecules. Molecular. Now, in the case of these crystals, these are not ions, they're atoms or molecules. They could be nonpolar, they could be polar, but they're only going to be held by intermolecular forces. That's absolutely, absolutely the weakest particle attraction. Usually, remember, intermolecular forces are about 3 to 5% as strong as chemical bonds, and that is what is holding an ionic metallic and then a covalent network crystal together. So what makes covalent network so wonderfully unique? Well, it's called network for a reason. For example, in diamond, every carbon atom is bonded to 4 other carbons. And carbon is relatively small. So these are short, multiple bonds that extend throughout the whole diamond. So it is an extension of short, strong bonds, covalent bonds that extend throughout the entire solid. That just gives it extraordinary strength. So interesting, the majority of covalent substances are covalent molecular. They're just held by intermolecular forces. They're super weakly held together. However, covalent network are our strongest particle attraction. All right, so if you're given a formula, can you categorize what type of substance it is? We saw that in the last video. And then do you know the particle attraction that's responsible for holding these substances together? So metallic, that's going to be mercury cations amongst a sea of electrons. Ionic, that's going to be cobalt cations and fluoride ions that are electrostatically attracting, very strong. Covalent molecular, just going to be intermolecular forces. We'd have to look deeper. Is this a polar or nonpolar molecule? Which intermolecular forces could it have? Lund dispersion, dipole-dipole, hydrogen bonding. But we need to know that these collectively are the weakest, usually, compared to the others. All right, then where do we go with properties from there? Well, they are related to the strength of the particle attraction. But before we get to those, I just want to show you some slides that just recap what we talked about. So if you want to pause and take a look at the information about ionic crystals. So I'm again categorizing what are the elements that make it up, some common examples, what are the particles that actually take on the unit cell position, and the force that's holding those particles together. Here's metallic. Then covalent molecular. Sometimes that's just referred to as molecular. And then covalent network. All right. If you want to pause and bring that a bit closer, here is just a nice kind of summary of the properties, and they're related to strength of particle attraction. I went ahead and laid it out here for us. And so we would categorize, since ionic is such a strong particle attraction, we would predict that their melting points of solids would be very high. Well, then their liquids should have high boiling points. It's going to take a lot of force to break them, so they're going to be hard. Where covalent molecular, notice the order I have these in, a little different than the other, but covalent molecular, they're held just by, intermolecular forces, and so they're going to be soft. We're not going to have to invest a lot of energy to break them, and they're going to have lower melting points. As far as electrical conductivity, something for now is electrical conductor if there are free moving electrons or free moving ions. If they're not, then we call it an insulator. Then it's not a conductor. So ionic as solids, no, they don't have any free moving electrons or ions, but they do conduct as liquids, because then you have the free moving cation and anion, and in solution. Most ionic compounds are soluble in water, and we'll see in chapters to come why then they are conductors in solution. Covalent molecular, non-conductors, no free moving electrons, free moving ions, neither with covalent network, but metallic, of course, the free moving electrons in the solid or liquid state. Metallic usually are non-soluble solids. Beneath this video, I will have another couple charts to share that I think beautifully also expand on these properties, which are all related to the particle attraction. But in essence, we need to be able to answer something like this. So if you're comparing two or more substances, the greater the intermolecular forces, the greater the particle attraction. I know we use IMF just with covalent, but we're talking about particle attraction. So the greater the particle attraction, the greater the boiling point, the more energy you have to invest to go from liquid to gas. The slower the rate of evaporation. Okay, that's where you're getting gas from liquid. Well, if you have to invest more energy because of greater particle attraction, it's not going to be creating a lot of vapor per a unit of time. The higher the particle attraction, the higher the viscosity, and the higher the surface tension. Here are some other questions that pull together looking at applying this whole idea of particle attraction. So I have the questions here if you want to pause, and I provided my correct answers over on the side if you'd like to see a couple examples of where this would come into play. So if you want to pause and take a look. And then 7 through 10. And then here is some on this page too. All right, so please check out the table that I have below this video. And it is surely our hope that these two videos, part 1 and part 2, accomplish these objectives for us.